So now let's prove that whenever we have a convergent sequence, then every subsequence of the sequence has to converge to the same limit. Now, this is an if and only if statement, and one direction is pretty clear. Why? Because if every subsequence of this sequence converges to the same limit, this means that the sequence itself, which is also the trivial subsequence, so to say, must converge to the same limit, right? So if every subsequence converges to the same limit, that the sequence converges, right, to the limit. And on the other hand, what's important is that we'll prove, so the importance of this statement is that essentially this sequence that is convergent has only one partial limit. So for example, we've already proved that the sequence -1 to the power of n cannot converge because it has two partial limits. It has two different subsequences which converge to different limits, right? So if the sequence converges, then it must converge to every subsequence of it must converge to the same limit. So let's prove it, right? So suppose that the sequence converges to a limit L, and then what we're going to use is that whenever we go far enough with the elements of the sequence, then the distance between the sequence and the limit is going to be as small as we please, and the same will hold for the subsequence, right? Because it's just sampling the elements of the sequence, right? So let's see how we formalize this. So suppose that we have a positive epsilon, then we know that for every positive epsilon, we can find n of epsilon such that for every index greater than this n of epsilon, we would have that the distance between the elements of the sequence and the limit is smaller than epsilon. Okay, so this is known. So how do we exploit it? So suppose that we have some subsequence, and we denote its index by k, so we have here a sequence in k. So I'll just remind you that the sequence of indices nk, right, it says the sequence n1, n2, etc., is a strictly increasing sequence of natural numbers, right? So what this means? This means that for every k, nk has to be greater than k. So for example, if k is 1, then the first sequence first index n1 has to be at least 1, and the second index n2, since the sequence must be strictly increasing, has to be at least 2, etc. So now, if we choose, so remember that the index of this sequence is actually k, right? So if we choose k to be greater than n of epsilon, then what we'll have is that, okay, if we choose for the same n of epsilon, for every k greater than n of epsilon, nk would also have to be by the definition of what a subsequence is, and k would have to be greater than k, right? And so it will have to be greater than n of epsilon. And therefore, by this condition we have here, ank minus l, since nk is greater than n of epsilon, this must be smaller than epsilon. And so indeed we have shown that for every epsilon, we can take this n of epsilon such that for every k that is greater than this n of epsilon, this index a and k, this element of this subsequence, its distance from the limit will be smaller than epsilon. And this proves our statement. This implies that this sequence a and k, whose like index is essentially k, right, converges to L. All right. So now let's prove another proposition. So suppose that we have a sequence that converges to some limit, and suppose that this sequence is smaller than some real number b, starting from some place, right? This is a bit relaxed condition, doesn't have to hold for every n, but starting from some point it has to hold. Then what we claim is that the limit of the sequence has to be smaller or equal than b, and the similar proof can be produced if an is strictly bigger than some a, then the limit has to be bigger or equal than a, right? I hope I said it clearly enough. So yeah, so the important thing is that if the sequence is smaller than some value, then its limit cannot be greater than this value. It will keep its bound, right? Starting from some place. So let's see how the proof goes. So suppose that the sequence an converges to some limit and its limit is greater than b. And we will essentially derive a contradiction here. And since we will receive a contradiction in this case, the contradiction would imply that the limit has to be smaller or equal than b, right? So How would we do it? Well, we would choose epsilon to be a minus b half divided by 2. And remember then by this assumption that a is the limit of the sequence an, we assumed that this limit is greater than b, therefore this epsilon is strictly positive. So far so good, right? And so let's see where we would derive a contradiction. So using this epsilon, we again use the definition of the limit. We would say that there exists n of epsilon such that for every n greater than n of epsilon holds that the distance between the sequence and its limit would be smaller than epsilon for every n that is greater than this n of epsilon. And now we remember that we chose epsilon to be a minus b half, right? Okay, and so now let's unwind this inequality, unwrap it. And so this inequality is essentially equivalent to saying that if we will take b here, then we can write b as b plus b over 2, right? Stupid way to write this, but bear with me. And now remember, we assumed that a is greater than b. We assumed it here. We assumed that the limit is greater than b, so the limit of the sequence is greater than b. Therefore, if I replace this b by this a, then this expression is going to be bigger than this expression. And now, essentially what we have is that, okay, we can write it in the following way. So it's a minus that. So if we make a common denominator here, right? So it's going to be 2a minus a, it's going to be a, and then minus b is going to be plus b. So we have an equality here by this identity. But this is, so why we did this, because this is epsilon half. So it's saying a minus epsilon half. And then this inequality essentially is equivalent to saying that, all right, an has to be greater than its limit minus epsilon and smaller than its limit plus epsilon, right? And so let's compute what we have on this side. So what this means, right, essentially this is already enough. So what this means is that for every n greater than n of epsilon, what we have is that a n is strictly smaller than b, starting from some place, right? So you could say, where is the contradiction here? But remember, we also assumed, on the other hand, we assumed in the proposition that an has to be smaller than b, starting from some place in 0, right? So to get the contradiction, we would choose lowercase n to be greater than the maximum of n0 and n of epsilon. And then for every n that is greater than this, we must have on the one hand, by what we proved, then that an has to be greater than b, because n is greater than n of epsilon. And on the other hand, since n is greater than n0, an has to be smaller than b at the same time, which is a contradiction. And this contradiction implies that a must be that the limit of the sequence must be smaller or equal to b. And let's see that this smaller or equal is actually a sharp bound, which cannot be approved. Okay, so let's see that. So this result cannot be improved, and let's consider an example. So suppose we have this sequence an, which is 1 minus 1 over n, then every element of the sequence is clearly smaller than 1. However, the limit, as we take the limit n goes to infinity, the limit is 1, right? So yeah, so the limit actually equals 1 and not smaller than 1. So this proves that the statement in the proposition cannot be improved. So it cannot be, we cannot expect it to be a sharp inequality at the limit. So at the limit, the inequality is becoming a weak inequality. Okay, so now let's prove this proposition. We've proved this in the previous lectures, but I would allow some redundancy for the sake of clarity in those lectures, because we're going to use this result later. So for clarity, I prove it again. So suppose that we have a convergent sequence that converges to some limit, then it's the sequence of its absolute values has to converge to the absolute value of the limit. And the proof is simple, because what we're going to do, again, we're going to choose positive epsilon, and then for every n that is greater than n of epsilon, we have that an minus L has to be smaller than epsilon on the one hand. This is the definition of the limit. And if we were to apply here the triangle inequality, which was also proved in previous lectures, then the triangle inequality implies that this expression is smaller than this one. And therefore, for the sequence of absolute values, we see that its distance from the absolute value of the limit is smaller than epsilon for every n that is greater than this n of epsilon. So for this sequence of absolute values, actually the same n of epsilon works and holds, right? So for the sequence of absolute values, we have shown that for every epsilon, we can take this n of epsilon, which exists for the original sequence, and then for every n greater than n of epsilon, we'll have that the distance of the sequence of sub-absolute values from the absolute value of the limit of the original sequence would be smaller than epsilon, which proves that this sequence converges to this limit L. Okay. And so note that the converse in general, so we have proved that if the sequence converges to a limit, then the sequence of absolute values converges to the absolute value of the limit. But the converse isn't true, because the converse in the sense that if we have that the sequence of absolute values is convergent, then the original sequence is convergent. This isn't true in general, because suppose that we take the sequence an, which is minus 1 to the power of n, then the sequence of absolute values is just a constant sequence, supposed to be inequality here, and so its limit is just 1, right? But the original sequence does not converge. It has two partial limits, and therefore it doesn't have a limit. Okay. But there is one circumstance where we can reverse the implication, and it is in the case that the sequence converges to 0. So if the sequence converges to 0, then on one hand the sequence of absolute values would converge to 0, and also if the sequence of absolute values converges to 0, it implies that the original sequence converges to 0. So let's just, we'll see it again later. So now let's define what it means for a sequence to converge to infinity. Basically, this means that the sequence is getting as big as we please, provided that we go far enough. So let's just see the formal definition, and then we will see a visualization of that. So suppose that we have this sequence, which, so we say that the sequence converges to infinity if no number is a bound for it, but it's even a bit more than that. If for every number that we choose, as large as we please, there exists some index that is dependent on this m, such that for every index that is greater than this natural number, every element of the sequence with index larger than that is going to be bigger than this number m. And remember, we can do it for every number m, right? And so in this case, we denote this, that the limit of the sequence at infinity is infinity. We also say that the sequence n diverges to infinity, or converges to infinity in the generalized sense, that is generalized convergence. Okay. So for example, let's see an example. So let's let h be some positive number and consider this sequence of real numbers h times n. Then the limit of the sequence is infinity, so indeed let's prove it. So essentially what I need to prove is that for every natural number m, every real number m, starting from some place, this sequence is going to exceed m. So let's see how I do it. So suppose that we have some real number. It could be like as big as we please, right? So let's choose n of m to be m divided by h, and then we take the integer value of that plus 1. So let's see how it works for this sequence. So now if we assume that n is greater than this n of m, then this n of m is this value, right? So n of m is defined as follows, right? It's m over h divide and plus 1. Yeah, there's a mistake here. So let's consider an example that would illustrate this. So for any positive h that is a fixed real number, we'll prove that h times n goes to infinity. This is also known as Archimedes' principle for natural numbers, that you can take any number as small as you please, and then you multiply it by any natural number, right? And as n grows to infinity, this would outgrow any number. And this limit will be also useful for us in the future in the current lecture. So let's prove this. And so indeed, for every real number m, we will choose n of m, like how far do we need to go, how large this n needs to be, so that h times n would be greater than this m, right? And so essentially the idea is the following one. In order for h times n to be bigger than m, then this n needs to be bigger than m divided by h, right? But since I want to give a natural index here, I will take m over h, I'll divide m by h, and then I will take the integer value of that. And that would have been almost good, except that we could have rounded this down. And so to account for rounding down, we'll add another 1 here. And so in this case, this natural number, any natural number that will be greater than this, will be for sure greater than m over h. So now let's see this in the proof. So now, if we take any n that is greater than this n of m, which is by definition that, so this number, since this is the integer value, so by taking the integer value, we can decrease this number by at most 1. It's going to be strictly smaller than 1 that we decrease it, right? When we round it down, we round it by something that is strictly smaller than 1. So as we add 1, we make sure that this natural number is strictly bigger than m over h. And now essentially, for every n that is greater than n of m, we would have that the sequence an is going to be, so since n is greater than n of m, then n is greater than that, right? So h times n, which is this, so h times n is going to be bigger than this number, right? Let me explain this once again. So our sequence an is h times n, okay? So if n is greater than n of m by definition is that. So h times n is going to be larger. If n is larger than this n of m, it's going to be larger than h times this number. But this natural number is bigger than m over h, as we explained. So the product is going to be m, right? So we have shown that for every n that is greater than n of m, an is going to be larger than m, okay? So now let's see another example. So consider the sequence, and we want to prove that it tends to infinity, right? So if you look at its first few elements, so for example, for 1, it's going to be like 2 over 1001, which is kind of small. And then for 2, it's going to be 5 over 1005. But then you will discover that the sequence grows quite quickly. So this 1000 has an effect for like at most the first 1000 elements. And then what we have here is going to be way, way larger than what we have in the denominator. But I don't want to go too deeply into that. Let's just prove this, that the sequence has to go to infinity, because obviously n squared grows much faster than n, okay? And so let's see how we would prove this kind of thing. So suppose that, well, we have some m, and we need to show that this expression can be made as big as we please. Okay, we're going to say that this is greater than n squared plus 1 divided by n plus n, but we're going to use some condition. For every n that is greater than 1000, right? If lowercase n is greater than 1000, then n plus n is going to be greater than n plus 1000. Therefore, in this fraction, the denominator here is larger than here, right? Because it's all positive. So the denominator here is larger than here, and therefore this fraction is smaller than this fraction. Okay, and then if here in the numerator we're going to remove this one, then we're clearly decreasing the fraction, right? So we're going to have that this fraction is greater than n squared over 2n. So it's greater than n half, okay? And so if we want this to be bigger than m, right, then n must be greater than 2m and also greater than 1000. So let's see how we do it. So first of all, yeah, what I said at the beginning, so for every n that is greater than 1000, this inequality, this chain of inequality is valid, okay? So if we choose n of m now to be the greatest of the two, the maximum of 1000 and 2m integer value plus 1, then for every n that would be greater than of m, we would have that since n is greater than of m, it is clearly greater than 1000 because it's greater than the maximum of the two. Therefore, this chain of inequality holds, right? So for every n greater than n of m, which is defined this way, n is also greater than 1000. So this expression is going to be larger than that. And then, since n is also larger than n of m, then it's also going to be bigger than this, right? So yeah, so as I said, since n of m is greater than 1000, those transitions are valid. And now, once again, so we have this transition, this is valid because n is greater than 1000, but n is also greater than n of m, which is greater than this number, 2m integer value plus 1. So it's going to be greater than that, right? And here again, we took this number, we could have rounded it, and so we could have decreased it by something that is strictly smaller than 1. So adding 1 here, we make sure that this expression is strictly greater than 2m. And as we divide by 2, we get that this is m. So essentially we have shown that for every m, as big as we please, we can find this natural number n of m. We can compute it this way, such that for every n that is greater than this n of m, this expression is going to be greater than m, which shows, according to definition, that the sequence converges to infinity. And now let's see a visualization of that. So if we were now to look at this sequence that I defined in Desmos, so an is n squared plus 1 and over n plus k here. And so k was in the original sequence, it was 1000. But then, you know, taking this sequence, this k too large, makes it harder to see the essence. So we'll pick a small k, like, for example, I don't know, 10, okay? And then we choose n of m to be the maximum between this k, which previously was 1000, but essentially for every k, n of m must be greater than k for all the transitions that we saw to work, and the integer value of 2m plus 1. And then basically what we see here, if we were to zoom in, so now let's take small m, right? So suppose for now that m is 1, okay? So we want the elements of the sequence to be greater than 1. So n of m is shown here in green. So it says that for every index here, starting from 10 on, all the elements of the sequence are going to be larger than 1. So here we have that they're larger by like a very big margin, but we don't care. The important thing is that for every m that you give me, I can show you how far you need to go so that all the elements of the sequence starting from this place are going to be greater than this m. And if I were to increase this m, then basically this formula says how to compute this n of m such that for all the indices after it, all the elements of the sequence are going to be larger than this m. So if I were to increase m, it's ran away quickly, so let's just zoom out. Let's just zoom out. Yeah, basically, you see the trend. I can increase m as big as I please. For example, m is 200, right? And then basically this formula says, okay, starting from this place on, from 400, for example, in this case, starting from this place on, all the elements of the sequence are going to be larger than m. And as we see here in this way that I computed in this bound, they're larger by a very large margin, but we don't care. The important thing is that all the elements of the sequence starting from this place on are going to be larger than m, and as we can get the expression that this sequence grows indefinitely, right? it can get as big as we please. So for every m that we choose, right, if we go far enough after here, all the elements of the sequence are going to be larger than this m, and this can be done for every m. Every large number that you give me, if you go far enough, all the elements of that sequence are going to be larger than that. So I hope it clarifies this. So now let's prove some more properties of infinite limits and sequence that converge to infinity. So suppose we have a sequence of real numbers which is non-zero. Every element of the sequence is non-zero, and the sequence converges to 0. Then 1 over n, the sequence 1 over the absolute value of n, would have to converge to infinity. Okay, so here, of course, since n is non-zero, then the absolute value of n is strictly positive, and there is no danger of dividing by 0 here. That's the reason that we demand that all elements of the sequence are non-zero. All right, so let's prove it. So suppose we have some real number m, as big as we please. So we might as well assume that m is positive, because, you know, it's interesting only for large numbers. So any negative number would be smaller than every positive number. So we might just assume that m is positive to begin with. And then we can choose epsilon to be 1 over m. And so, of course, this epsilon is strictly positive because m is positive. And why do we need to use epsilon here? We want to use epsilon because we want to exploit the fact that we know that n converges to 0, right? So then there exists this n of m, which essentially this n of epsilon, right? Because epsilon is defined in terms of m, or m is defined in terms of epsilon. So we can say that this n of m is essentially a function of epsilon, right? And so that so this n of m is what we need to show that the sequence of 1 over the absolute value of n converges to infinity. But we know that there exists, for this epsilon, there exists n of epsilon such that since the sequence n converges to 0, the absolute values, and it's non-zero, then its absolute values are going to be strictly positive for every n. And on the other hand, since this converges to 0, then this minus 0 in the absolute value, so I wrote it this way, is going to be smaller than epsilon, which was chosen to be 1 over m. And this is for every n that is greater than this n of epsilon, which is essentially this n of m, right? So essentially we've proved that for every n, there exists this number n of m, such that for every n that is greater than n of m, we would have that the absolute value of a n would be greater than 0 and smaller than 1 over m. And now, since everything is positive here, this is equivalent to saying that 1 over an is strictly bigger than m for every n that is greater than n of m, which means that we've proven by definition that the sequence 1 over the absolute value of n converges to infinity, because for every n we show that there exists a number, natural number n of m, such that for every n that is greater than n of m, this sequence is greater than m, so it means that the sequence converges to infinity. Okay. And so let's see an example of non-convergence. So for example, we can consider this sequence, and this sequence does not converge to infinity. So it's in a sense that if a sequence converges to infinity, then every subsequence of the sequence must also converge to infinity. And so let's see what fails here. So the thing that fails here is that no matter how far we go, right, we're always, so suppose you chose any m. So suppose you chose m equals to 1. So if the sequence were to converge to infinity, then starting from some place, all the elements of the sequence must be greater than this one, right? This is the definition. But the thing is here that no matter how far we go, we'll always find an element of the sequence which is 0, and therefore is going to be smaller than this m. So the definition doesn't work. And so let's see this formally. So the sequence, if you want to write this as an, so an is 0 for odd n's, and it's n over 2 when n is even, as you can verify. This is a better definition of the sequence. And now, for every m, so for example, say m equals 1, and every n that is greater than 1, we can choose the natural number for n plus 1, which is this large odd number, which is greater than n. We have for every n that is greater than this n, right? We have that an, which is a for n plus 1, is 0, and so it's going to be smaller than this m. So what happens here is you chose some m, you choose m to be 1. And it just so happens, so no matter how far you go, you can never ensure that all the elements of the sequence are going to be greater than this m. Okay, I hope it was clear enough. So on the other hand, the sequence is also unbounded, because for every m that is greater than 0, we can find this n, and this is n of m, n. So if we choose this n, then this element of the sequence an with this index n is going to be the integer value of m plus 1, which is going to be larger than m. So this sequence is on the one hand unbounded, as we've shown, because no real number can bound it above, right? For every real number, you can always find an element of the sequence that is going to be larger than this m. So on the one hand, the sequence is unbounded, but on the other hand, we see that it is not enough to say that the sequence converges to infinity, because it does not converge to infinity according to definition. Why? Because no matter how far you go, you can always find an element of the sequence which is smaller than 1, right? So the definition doesn't work, doesn't apply in this case. So despite the sequence being unbounded, the sequence does not converge to infinity, does not tend to infinity. And we can see, let's consider another example. So consider this sequence, n plus 1 over 2 when n is odd, and minus n over 2 when n is even. So as you've probably guessed, the elements of the sequence, if they're written one after another, this is this sequence, right? So the sequence does not converge to infinity, but it has a subsequence that converges to infinity and some sequence that converges to minus infinity. However, the sequence of absolute values do converge to infinity, as you can easily verify, and I would leave this as an exercise, which is supposed to be quite easy if you followed so far. All right, so now let's prove another proposition. So suppose we have a sequence such that in an absolute value, so this is kind of the reciprocal of the theorem that we proved previously. So if the sequence of absolute values converges to infinity, then this sequence 1 over an has to converge to 0. And it's important to say that all the elements are non-zero. Sorry, I didn't mention here, but all the elements are non-zero. And so this is a proof. So suppose that we choose a positive epsilon here, right? Then there exists n of epsilon such that for every n that is greater than n of epsilon, we would have that an would be larger than 1 over epsilon, because essentially you can think of this 1 over epsilon as m, right? So no positive real number can serve as a bound for the sequence because it converges to infinity. So this means that starting from some index that depends on epsilon, all the elements of the sequence of the absolute values is going to be larger than 1 over epsilon, which is equivalent to saying that since everything here is positive, that 1 over an in the absolute value, I wrote it in this way to emphasize that the limit is 0, but you can ignore the minus 0 so far. So this is equivalent to saying that 1 over an in the absolute value is smaller than epsilon. So this inequality is equivalent to this inequality. And it shows that for every epsilon, there exists a natural number n of epsilon, such that for every n that is greater than n of epsilon, 1 over an minus 0 is going to be smaller than epsilon, which proves that the sequence converges, 1 over an converges to 0. But again, it's important to say that all the elements of the sequence are non-zero, and the sequence of absolute values converges to infinity. Okay, so this proves, according to definition, that 1 over an converges to 0, right? Okay, and now we're going to prove this very useful proposition, which is called the Bernoulli inequality. And it says that for every natural number n and every real positive h, we have the following inequality. 1 plus h to the power n is going to be greater or equal to that, and this is just a straightforward consequence of the binomial formula. So we may assume that n is greater than 2, because for n equals 1, it's obvious 1 plus h is greater than or equal to 1 plus h. So we might just assume that n is greater than 1. So by the binomial expansion, we obtain that 1 plus h to the power of n is this 1 plus n choose 1 times h, right? And then the other terms is just sum as k goes from 2 to n choose k, h to the power of k, right? So this is why it was important for me to say that n is at least 2. So n choose 1 is just n. And then we have here, since h is positive, is just positive terms. So all of it is going to be just greater than 1 plus nh, okay? And so for positive h, we could terminate this actually at every place that we wanted, but it turns out that this inequality is enough for most applications and it's very useful. But of course, we could have better inequalities such as this one, or even this one, right? But we chose to terminate it here. But essentially, we could have derived here like this n inequality of this type, right? So to say. But this is enough for lots of applications. Okay, so now let's prove another proposition. Suppose we have two real sequences such that bn is greater than an starting from someplace. Then if the sequence an converges to infinity, then bn must converge to infinity, and the proof is quite straightforward, because the n of m that is going to work for this sequence is also going to work for this sequence. So let's just see the formal proof. So let m be any positive number. Since an converges to infinity, it follows that there exists n1 of m such that for every n that is greater than n1 of m, an is greater than m. This is just the definition of an converging to infinity, right? So now we choose n of m to be the maximum of those two numbers. So it's because we're going to choose n that is greater than this n of m, and so it's going to be greater than this n0. And since it's greater than this n0, then bn is going to be greater than an. So now for every n that is greater than n of m, right? So this n is greater than n of m, which means it's greater than n1. So it means that an is greater than m. And it's also greater than n0, which means that bn is greater than an. So it shows that for every n that is greater than this n of m, bn is also larger than m, which proves, right, so that's for every n that is greater than n of m, we have that bn is greater than m, which proves that bn also converges to infinity. Okay. So now with the Bernoulli inequality, we can prove this quite useful limit. So if we consider the limit of q to the power of n, so if q is greater than 1, it's natural to expect that this would, the limit would be infinity. If q is 1, then it's just constant sequence of 1s. This is going to converge to 1 because it's a constant sequence. And then for q smaller than 1 in the absolute value, we'll use, again, here the Bernoulli's inequality to prove that this would converge to 0. So I would say that this is the less trivial result of all of those. And then if q is smaller or equal to -1, the limit doesn't exist. This is also quite straightforward because the sequence is going to have infinitely many positive elements and infinitely many negative elements, so the limit does not exist. Okay, so proof. So if q is greater than 1, there exists positive h, and such that we can write q as 1 plus h, and this h is essentially 1 minus q. Sorry, it's q minus 1. Damn it. Alright, so now let's prove it. So suppose that q is greater than 1, then we can find a positive h such that we can write q as 1 plus h for this positive h, and of course this h is just q minus 1, and since we assume that q is strictly greater than 1, then q minus 1 is strictly positive. And therefore, q to the power n is this 1 plus h to the power of n, right? And using Bernoulli's inequality, which we've just proved, it follows that this is greater than 1 plus an h. And since we have proved that the sequence n times h, even by definition, goes to infinity, then 1 plus the sequence is strictly bigger for every n than the sequence that goes to infinity, and therefore another proposition that we proved shows that such a sequence converges to infinity. And therefore we obtain that for q that is strictly bigger than 1, q to the power of n is bigger than the sequence that converges to infinity, therefore, for every n, right? Therefore, q to the power n converges to infinity, or yeah, the limit is infinite. Okay, for q equals 1, then q to the power n is basically a constant sequence of 1s, and therefore its limit is just 1. This is pretty clear. And now suppose that q is strictly smaller than 1 and strictly bigger than -1. Then the absolute value of q is strictly smaller than 1, and so we will prove that the sequence of absolute values converges to 0. And this would imply that the original sequence must also converge to 0, again by a proposition that we have already proved in this lecture. So yeah, and this would imply that the original sequence goes to 0. So now let's see. Yeah, so if q is 0, then clearly we have a constant sequence of zeros. Therefore, in this case, q to the power n clearly converges to 0. So now we will assume that the absolute value of q is strictly positive and strictly smaller than 1. I mean, strictly positive is strictly bigger than 0, right? The absolute value of q is non-zero. And therefore, 1 over q would be bigger than 1. Therefore, what we have proved that this sequence, since this is bigger than 1, then we have proved that this has to go to infinity, right? So this limit is infinite. And this is the same sequence, we just can drag the n over here by properties of powers. Now, using the proposition that we've proved earlier, that if a sequence goes to infinity, then 1 over the sequence goes to 0, right? So the sequence 1 over the sequence that we have already proved that this sequence goes to infinity the limit of this sequence is 0, but on the other hand, 1 over the sequence is just this sequence for every n, right? And therefore, q to the power n for q whose absolute value is strictly smaller than 1 converges to 0, right? And so if q is strictly smaller than -1, then q to the power n would contain infinitely many positive elements and infinitely many negative elements, and therefore the limit of such a sequence does not exist. Okay, so now let's prove another important property. If we have a positive real number, then the n's square root of a is 1. The limit as n goes to infinity tends to 1. You've probably played with the calculator when you take a positive number and you take its root repeatedly, and then you see that very quickly you get values that are getting very close to 1 until the values on the calculator just stabilize at 1, right? So let's prove this. So if a is strictly bigger than 1, then by the properties of real numbers and square roots, right, the n's square root for every n of a must be bigger than 1. Why? Because if it was the case that this square root was smaller than 1, then taking a power of a number that is smaller than 1 would give any power would be smaller than 1. And therefore, this shows that the nth root of a for every n has to be strictly bigger than 1. Okay, so now we can write this square root, n square root, as 1 plus something positive. And basically we want to show that the sequence hn, which is this is a positive sequence, right? We want to show that its limit is 0 as n approaches infinity. And for that, we're going to use the sandwich theorem. So if we were, right, so on the one hand, a is 1 plus hn to the power of n. This is just the definition of hn. So 1 plus hn is the n's square root of a. Then taking the n's power of that, we obtain a on the one hand. And on the other hand, using Bernoulli's inequality, we get that this is bigger than 1 plus n times hn. And remember that hn is strictly positive. Therefore, it works. So now basically, this inequality implies that hn is smaller than a minus 1 over n. But remember that a is some constant that is greater than 1. And therefore, as n would go to infinity, this would go to 0. But on the other hand, so this means on the one hand, hn is non-negative, and on the other hand, this is smaller than this sequence, and this sequence converges to 0. And now by the sandwich theorem, it follows that since this limit is 0, sandwich theorem implies that hn goes to 0, which proves that the nth square root of a is just this limit of 1 plus hn. As n goes to infinity, this goes to 0. Therefore, by the limit arithmetic theorem, this limit exists and equals to 1. Okay, so now what about a that is smaller than 1 and greater than 0? Again, we're going to apply this trick. Of course, for the nth square root to be defined, at least over the reals, we must have that a is positive. Okay, so now if we were to look at 1 over a, so if a is strictly bigger than 0, then 1 over a is strictly bigger than 1. And the nth square root of this sequence, by what we proved just now, the limit of this has to be 1 on the one hand. On the other hand, using the properties of square root, we see that we're computing the limit of this sequence, which implies, by the limit arithmetic theorem, since every element here is non-zero, right? Basically, this implies that this limit exists by limit arithmetic theorem, and the limit is 1.